before we really talked about conjugation, we still had seen a lot of carbocations. And we had already ranked carbocation stability of kind of non-complicated examples. What we said is that like a methyl carbocation doesn't have anything stabilizing it. It's the least stable. That would be less stable than a primary carbocation. That'd be less stable than a secondary carbocation. And that's less stable than a tertiary carbocation. So examples of these, the methyl carbocation is pretty straightforward, but this would be a primary carbocation. This would be a secondary carbocation. So, and then a tertiary carbocation would be on a tertiary position. So, what's new now? Now we know that what stabilizes things? Things are stabilized when they're delocalized. A positive charge on a single carbon is less stable than a positive charge distributed over multiple atoms. So where does that relate to conjugation? Well, we said that in the last video that the allylic carbocation was stabilized because it was delocalized not just on that carbon, but also on the other carbon. So in reality, this kind of seems like it's a primary/primary carbocation. And what does that do to its stability? Well, now it's essentially like instead of one carbon holding all of the thing that makes it unstable, now it's shared over two carbon atoms. And because of that, it actually becomes more stable than a secondary carbocation. So I'm going to just erase, and you could just kind of put it in between here. We'll put it, actually, instead of erasing, let me just kind of mark down here that a secondary carbocation is less stable than a primary allylic carbocation. We'll call it a primary allylic carbocation. And that's what this species is here. It's primary, and it's allylic. Okay. What else could this be like? Well, this is primary. It doesn't always have to be primary when things are delocalized and conjugated together. It could have more species around it as well. So what if we had a carbocation like this, where this is technically a secondary carbocation as we have it shown right here, but just like this primary allylic species, these electrons are delocalized. They're conjugated with that empty p orbital to show that there's also carbocation character on that secondary position. So this would be a secondary allylic species, and this is actually, and we'll write that in here, secondary allylic. And it turns out that that is roughly the same energy as a tertiary carbocation. So we're going to write here about the same, so we'll put that symbol as a secondary allylic species. So it could get even more stable from there. There's another methyl group coming off of there. It would be a tertiary secondary allylic, which we could then say obviously that it's going to be more stable than either of those. So that is how conjugation stabilizes these carbocations, and we can see it based on this electrostatic potential map in your packet. So over here we have a localized carbocation. The blue color is where it shows that it is electron poor, and we see that it is entirely localized just on this carbon on the right, the one that has that positive charge. Compared to this primary allylic carbocation, really it shows that blue color is delocalized between both of those primary positions. So this shows with computational chemistry exactly what we said here with just structures on the board, that the delocalization through this conjugation really stabilizes the carbocation. So that is a new outlook on carbocation stability.